Good afternoon, students. Today I will discuss on the next part of the chapter, that is equilibrium. Last day we have discussed on the buffer capacity or buffer solution. Okay, can you see the video? Can you see the video?
Yes.
Very good. So let's come with a pen and paper with you. Come with pen and paper with you because it will help you to concentrate on the study. Take a pen and paper with you. Very good afternoon to everyone. Can you remember what is buffer solution? Can you remember this? What is buffer solution? Ankon Spondon, those who are online. Yes. One example of buffer solution or the types of buffer solution. Types of buffer solution or one example of buffer solution. So not only weak acid, there is something with weak acid. No, not weak acid. NaOH is not an weak acid, it is a strong base. Yes, weak acid and its salt. Buffer solution, that is weak acid and its salt. Weak base and its salt. These are the two types of buffer. Clear? Now weak acid and its salt, it is called acidic buffer, and weak base and its salt, this is called basic buffer. Acidic and cannot see the board clearly, very problem. Very small area of the board can be seen. I cannot move the board. I can move the camera. Okay. Okay, I am writing down in this portion which is visible to you. So, weak acid and its salt, weak base and its salt can work as an buffer solution. Now, next, that is how the buffer works, it is known to you. How the buffer works, is it known to you? For example, NH4OH plus NH4Cl, it is an example of buffer. Now, how it works or how it restricts the change of pH. So, for this we may write the dissociation equation NH4 plus OH minus and NH4 plus Cl minus. Now, we are adding acid to this solution. We are adding acid externally to this solution. Now, what happened? Acid H plus will combine with the OH minus, which is dissociated from the NH4OH, producing H2O. Now, we know H2O is an weak electrolyte, so the pH retains the same. If we take NH4Cl and NH4OH and adding OH minus, then how it restricts the change in pH? That OH minus, the concentration of the OH minus in the right side of the equation will be higher. So, we know the La's-Atelier principle. How many of you can remember what is La's-Atelier principle? It is La's-Atelier principle. According to the La's-Atelier principle, the first reaction will move in the backward direction. We will move in the backward direction, so that the there will be the production of NH4 will be higher. So, it will, by this way it can maintains the pH. Yes. So, next stage is the solubility. It is the next point, it is the solubility. Next, it is what is solubility. Now, from the general idea, we can tell that solubility is the process of dissolving a substance on a solvent. Now, the substance which we want to dissolve is called as solute, and in which, that is the solution in which we want to dissolve it, that is it is called a solvent, and the combination of these is called the solution, right. So, the solution is the solute plus solvent. Now, the solubility, there are some specific points are there, that is we have to remember this. What is this? First of all, an amount, temperature, these are very important. Suppose in 100 gram water, 25 gram of sugar can be dissolved at 10 degree centigrade. At 100 gram of water, in 100 gram of water 25 gram, it is the maximum amount, it is the maximum amount of sugar can be dissolved at 10 degree centigrade. So, this is the process of solubility. So, it can be defined as the maximum amount of solute can be dissolved in 100 gram of the solvent at a particular temperature. This is called the solubility. Okay. Now, next point, what is solubility product? What is solubility product? Now, the solubility product is defined as, it is the product of the concentration of the cations and anions form to the power of its number. The solubility product is the product of the concentration of the cations and anions form to the power of its number. For example, if we take Ax, by. Now, the dissociation equation for this, it is equal to x a y plus y b x minus. So, y plus x is the number of A, y is the number of B, y is the valency of A and x is the valency of B, right. So, it is the general equation. Now, for this Ksp for this equal to the concentration to its power, that is A y plus to the power x into B x minus to the power y. So, it is the concentration and to this power. So, in this way we can calculate the Ksp of any sparingly soluble salt. So, it will be easier if we go with an example. Now, before that, the solubility product is for sparingly soluble salt. Solubility product is for sparingly soluble salt. What is sparingly soluble salt? Now, sparingly soluble salt, the definition is that the negligible amount of salt can be dissolved in any medium or any solvent is called an sparingly soluble salt. That is negligible amount. What is the range? That is 1 into 10 to the power minus 5 or 10 to the power minus 6 gram. This is called the negligible amount in 1 liter of the solvent. So, when a salt is dissolvable in a solvent in the value that is 10 to the power minus 5 or 10 to the power minus 6 to its power is called its solubility, a sparingly soluble salt. Now, next one, that is what is the example. For example, AgCl. So, first of all, write down the dissociation equation, that is Ag plus Cl minus. It is assumed that the solubility is S mole per liter. Solubility of AgCl is S mole per liter. Solubility of AgCl is S mole per liter. So, the concentration is also S and here also S. Ksp, that is equal to the concentration of Ag plus into concentration of Cl minus. So, the concentration, that is S into S, Ksp equal to S square. So, it is the relation between the solubility and solubility product. Clear? It is the relation between solubility and solubility product for AgCl. If we took any other example, that is PbCl2, for PbCl2 Pb2 plus 2Cl minus. Now, the solubility of PbCl2 is given as S. So, the concentration becomes S and it is 2S. We have done it earlier, why it is 2S. Now, Ksp, that is Pb2 plus into Cl minus square. So, Pb2 plus having S, now Cl minus having concentration 2S, the power is square. Now, follow here for PbCl2, the Ksp can be represented as Pb, that is number of the valency here, the valency of Pb here, that Axby, for Axby we have written that is Xay plus Yb x minus. Now, x, here x, that is 1, here y equal to 2. So, if we put in this way in this equation, then we will get the PbCl2, that is here A equal to Pb, y is the valency of B, that is the valency of, that is 2, and here Yby minus, y is the number of that is the number of B, that is 2. It will go in the power of that is Cl minus square. So, this way by using general equation we can solve it. Now, coming to that section, that is it is equal to S into 4s square, that is 4s cube, 4s square, that is 4s cube, Ksp, that is equal to 4s cube for the salt like PbCl2. Okay. Have you understood? Students, have you understood this? Okay. So, we may take any another example regarding that to derive the relation between Ksp and S. Suppose Al, aluminum hydroxide. So, first of all, writing down the equation Al3 plus 3OH minus. Okay. Now, the solubility is given that it is S. So, the concentration will be S, and here it will be 3S because 3 moles of OH is formed. So, 3 multiplied by the solubility, that is it will be the concentration, that is 3S. Now, Ksp, that is equal to Al3 plus OH minus to the power 3, it is S, it is 3S cube, that is 27 S to the power 4, that is Ksp equal to 27 S to the power 4 for an example of aluminum hydroxide. Okay. So, in this way we can calculate, yes, very good, 27, very good, Ankon, you have cultured this. Okay. Now, what is the application of this? What is the application of solubility product, or what is the application of the buffer solution? What is the application of solubility product? Now, there is a theory is that when a compound or when a substance deposited, that is when a substance precipitated, then what happens? The solubility product, that is the concentration of the cations and anions, must be greater than its Ksp, very important. The concentration of the cations and anions when exceeds the value of Ksp, then the salt deposited, it is the form, that is the formula. So, when the individual concentration, that is the concentration of the product becomes greater than that of the Ksp, then the salt deposited in the form of precipitate. Now, in qualitative chemistry, what happens? We have precipitated the salt, the cations in the form of a PPT. Now, for PPT, the importance is that here every time we have to exceed the value of solubility product. So, the solubility product must be exceed, that is the individual concentration of cation and anion must be exceed than that of the solubility product, and then the salt will deposit. And what is the use of buffer solution in the qualitative analysis? So, in group 3 of qualitative inorganic analysis, there we used NH4Cl plus NH4OH, the basic buffer, just to maintain the proper pH of the medium, because we want to deposit in 3, that is iron, aluminum in hydroxide form. So, the proper pH should be maintained for this. Another one, in the case of in the group 5, that is we use ammonium carbonate and ammonium chloride. In group 5 ammonium carbonate plus ammonium hydroxide. Here in group 5 we have used barium strontium, calcium, these two precipitate. Now, these are precipitated in the form of carbonate, here they are precipitated in the form of hydroxide group 3. So, we maintain there a proper pH, so that the precipitates will come out in the correct form. So, next step we have to move to some problems regarding to the solubility product. Okay. So, everyone have pen and paper with you. I am writing the problem in the board first and then I will solve it. The solubility of AgCl in the solubility of AgCl in the solubility of AgCl in water at 298 K, in water at 298 K equal to 1.06 into 10 to the power minus 5 mole per liter. Calculate solubility product. Calculate solubility product. How we can solve it? So, first of all, AgCl, very simple form, that is Ag plus Cl minus. Okay. The concentration, assuming S, it is also S. So, Ksp equal to concentration of Ag plus Cl minus, that is equal to S square, correct. Now, Ksp, that is equal to S, that is the value of 1.06 into 10 to the power minus 5 square, that is equal to, we have to calculate 1.1 into 10 to the power minus 10. Clear? Is it clear? Is it clear to you? No, sir. Very good. I am repeating this once. Have you written the problem? First of all, no, sir, then yes, sir. I do not understand what you have written this. Okay. Okay, so I am moving to one more example, that is one more problem. The solubility of calcium fluoride in water, the solubility of calcium fluoride in water is equal to 1.7 into 10 to the power minus 3 gram. The solubility of calcium fluoride in water is equal to 1.7 into 10 to the power at 298, 1.7 into 10 to the power minus 3 mole at 298 K. Per 100 ml of solution, per 100 ml of solution, very important, because only 100 ml is given here. Calculate the solubility product of CaF2. calculate KSP of CaF2. Okay, this is the problem. Now it is given in 1.7 into 10 to the power minus 3 in 100 ml. So in 1000 ml it will be multiplied by 10, that is 710 into 10 to the power minus 3. Now this small amount can be dissolved in a 1000 ml of the solvent. Now what is the solubility? How we can calculate the solubility of this? Now the solubility can be calculated as by the, we have to calculate the molar mass of CaF2. Thus calcium having molar mass 40 and fluorine having the 19. So 40 plus 19 into 2, that is 38, that is 78 gram. That is 78 gram is the molar mass of calcium fluoride. Now we have to divide this value, that is the solubility divided by molecular mass, to calculate the solubility in gram. The data will be 17 by 78, that is equal to 2.18 into 10 to the power minus 4. by 78. We have to solve it. So 2.18 into 10 to the power minus 4, it is the solubility. Now we have to move to the solubility equation. So write down the solubility equation, that is Ca2 plus F2 minus CaF2, that is Ca2 plus 2F minus KSP, that is equal to Ca2 plus concentration into F minus concentration square. Ca2 plus, that is 2.18 into 10 to the power minus 4, F minus 2 into 2.18 into 10 to the power minus 4 square. into 10 to the power minus 4 into 2 into 2.18 into 10 to the power minus 4 square. It will be 2.18 into 2, that is 4, 2 into 4.36 square into 10 to the power minus 8 into minus 4 10 to the power minus 12, 4.36, it will be equal to round about 33 into 10 to the power minus 12. We have to calculate this, then we will get the answer. Problem written: solubility per gram mass. Solubility per gram mass equal to this value, that is 2.18 into 10 to the power minus 4. I have calculated there, that is 17 into 10 to the power minus 3 divided by the 40 plus 38, that is 78. It will be equal to 2.18 into 10 to the power minus 4. Okay, it is one of the difficult problem. Have you completed this? Okay, write down one problem. pH value of a saturated solution of barium hydroxide is 12. pH value of a saturated solution of pH value of a saturated solution of barium hydroxide. pH value of a saturated solution of barium hydroxide is given is 12. Calculate solubility product is 12. Calculate Ksp of barium hydroxide. You will try this problem at your home. HW. Okay, so write it down first that pH value of a saturated solution of barium hydroxide is 12. Now calculate the Ksp. It is very simple. First write down the equilibrium equation, and from there you will get the concentration of OH minus, and pH is given, that is 12, that is POH will be 14 minus 12, that is 2. So, in this way we have to start. So, meet you again in the next class. So, everyone, bye.